Hello everyone, welcome back to the latest lecture session. Until now, I guess we covered a bit more than half of the content that we wanted to cover. So the course obviously is wastewater, half of it, water, the other half of it. Wastewater, our needs and objectives are different. In the context of water, obviously the objectives are different. Let's look at what it is that we did in the context of wastewater. A quick summary. What do we have? We have, what do we say, particles like cloth rags and so on and so forth. We have heavier particles like grit, inert particles which will settle pretty fast. So preliminary treatment, right? And then we have suspended particles in the wastewater, primary treatment, gravity is our friend. And then we have mostly soluble COD or BOD, and we use the bacteria or nature as our friend. We supply oxygen, we degrade it meaning the BOD or the organic content, and we form flock forming bacteria or microorganisms, pardon me, and they form flocks, are heavier, settle down. And then we looked at nitrogen and phosphorus removal, yes, and then we looked at disinfection. Obviously relatively more, what do we say, encompassing. In the context of water, what is it that we are concerned about? So depending on the source, obviously you can have what do we say, toxic compound present or such, then the kind of treatment mechanism that you would choose would obviously be different. But we are obviously going to look at the general cases while covering the different kinds of techniques that you can use or modify or employ according to the needs. Overview, where do we get the water from? Typically surface water, if surface water or good quality surface water is available. In general, with respect to or considering the water stress in India, good quality surface water or even surface water of any quality is not usually available. So people end up, what do we say, drilling personal, municipal, not municipal, groundwater pumps or pumps to pull out or pump up the groundwater and use it. But in quite a few municipalities, you still have piped water drinking water being distributed, let's say 1 hour in the morning, 1 hour in the night and such. So let's look at the principles, and hopefully, in the coming decade, we will be in a much better off position. Let's see where we are. So when I'm going to design a plant, a water treatment plant, right? Earlier we used to call, with respect to wastewater, we used to refer to the plant as sewage treatment plant, sometimes as wastewater treatment plant. Again, different people, different ways. I am going to call this drinking water treatment plant as WTP. Fine. Okay, water demand, right? That's something that we need to be able to look at. So why do I need to do that? Obviously, I need to know what is it or how much capacity should my plant be able to cater to, or what should be the capacity of my plant. So for that, obviously, what do I need to do, or what do I need to consider? For example, I can look at the need right now and build a plant, but the plant construction itself might take 2 years, and then the population might increase, might decrease, but rarely, at least stagnant or increase, and then I will be left with a redundant plant pretty soon in 5 years. So I am going to plan ahead, let's say 30 years typically, let's say, or 25 years depending on the relevant availability of capital or the growth in that particular area. So how long, let's say 20 period, 30 period design period is something I need to consider, how far into the future. Once I do that, I then need to see what will be the population that's expected within this particular area that I'm trying to cater to, right? So then I need to be able to estimate the population, and here comes the tricky part. People crunch numbers, so on and so forth, but human beings, they typically don't follow or don't fit the patterns described by a set of formulae. Depending on social conditions, economic conditions, you are going to have growth. You can have, what do we say, people leaving the community and such. But again, these are aspects that we need to look into. In general, we look at the trends in the recent past and use that as an estimate. Obviously, we also have, what do we say, some indication based on the kind of growth it has witnessed in the recent past. that can be an indicator. We always obviously are going to look at the census data, and then we have the 3 or 4 formula that we use. But again, keep in mind that the formula are only indicators. Rarely will people depend only on these formula, let's see. So that's something to keep in mind. So what have I done? I am now looking at, let's say, 25 period as years as my design period. I am able to estimate the population that will be present in this community or locality 25 years down the line. What else? I need to look at the expected, water demand per person or per capita, right? And then I will be able to calculate the relevant needs. And that's what I guess we have here: demand period, population, and how much, right? So time, number of people per person, how much is it that they are going to consume. After this, I also need to consider, contingencies. Let's say fire. That's one aspect for which people always have to design. And another aspect is, again, you are going to have variation in flow or the need for water during the day. For example, we saw pretty good graphs in the context of wastewater, where how sewage was being generated and how you had higher, water inflow into the sewage treatment plant around 11 or 12, because people wake up at 9 or let's say 8 o'clock, and then morning ablutions and water is discharged. If water is being discharged, they will also need water. So obviously, as we look at our day, we will use much more water in the morning, some during the afternoon, and again some during the night. So again, there will be variation in water demand every day. So that's something we need to consider, right? So these are the 4 aspects we typically consider. Let's see. Let's move on. Design period. So the time period for which the facility will be able to meet the demand or the design capacity. So I'm concerned about what will be the design capacity. So how is it that I come up with what is this design period? So there are some thumb rules. Again, you can always or should always look at this CPHEUO manual for India. For different countries, they have their own guidelines or such. For example, in the US, I think different states have different guidelines. So that's one muddle there. So regulatory aspects, as in government guidelines, typically have to be considered. If there are any constraints, binding constraints, obviously that's one aspect. When I'm talking about design period, obviously population growth comes into the picture, right? As in, if it's being explosive growth, I can't, and if it's difficult to predict, again, that's another aspect. So rate of population growth is something that we are also going to look at when I'm looking at the design period. And it's not as if I can say that I'm going to design it for 100 years. Why is that? The structures that I build, be it the cement or the concrete structures, or the equipment that I use, mechanical and electrical equipment that I use, have their own lifetimes. So the cost of replacing them, maintenance, and certainly their lifetimes also come into picture when we are considering the design period. Why? That's tied up with how easy or difficult is it to expand. In general, in India, difficult to expand. Earlier or even now, we still try to have the water treatment plants outside the city, but with the rapid growth near the cities or in and around the cities, now we have the water treatment plants and even sewage treatment plants within the cities. So again, these are aspects that we need to consider. Why? Expansion due to lack of land or relevant aspects is going to be an issue. And more importantly, or equally importantly, I guess, so for example, my population growth is something like this, okay, and my design, so this is the year and this is the population. So let's say this is for the design, I'm designing it for this population, let's see, right? But as you see, for most of the time, or quite a significant fraction of the time, the population is pretty less. So during that particular period when there is relatively less or minimum hydraulic load, how will the plant perform, let's say. So that's also one aspect to keep in mind. I might not plan to capture this entire population growth with only one plant, maybe multiple plants later or such, yes, or standby areas or units which can be used or set up later, let's say. So different aspects come into picture when we look at the design period. So typical periods, we have, I guess, some information here which will give us an idea. So large dams, again, people think that these are, what do we say, going to be there forever, but again, as you see, it's 1 or 2 generations. Treatment plants with fixed facilities, the facilities, concrete and such, 20-25 years. The equipment 10 to 15 years, and distribution network, which is a much critical aspect, at least in my point of view, at least in India. So 20-25 years. As you see, they have their own lifetime. So your design periods obviously need to consider these aspects, let's say, right? So population forecast. So once I know, which year or until which year will I try to capture or cater to the needs of the relevant population in that community, I'll now need to calculate the population. So I'm going to estimate or forecast the population. So in general, the best way is to look at data, but I'll give you the example, let's say Ghaziabad, not Ghaziabad, pardon me, Greater Noida. So one of the more developed and relatively planned, what do we say, cities, if I may say so, mostly just what do we say, agricultural land earlier, but with the shift towards industrialization, obviously some people looked far ahead, and Greater Noida, at least they did. This was with respect to, or when they were planning for the NCR, that was way long ago. So what do we have now, or what did they have? They, divided into zones, different areas, different land, what do we say, population density per area, and group housing projects, and they estimated the water demand and such. But initially the growth was very less, and their distribution network too was patchy, or water distribution network or sewage capture or sewerage network too was pretty patchy, right? And later there was explosive growth, and also this growth was not something that was constant, as in when the economy was doing good, there was a floating population of almost 10 lakhs, and the water network, sewerage network used to be under remarkable stress. And then when the economy wasn't doing good, again people used to move out, again you had issues or such issues. So considerable, what do we say, issues or our aspects are at play. So again, it's not as straightforward as we look at. So population forecast, it's not as, what do we say, easy as we expect it to be from the formula or such. You have this, at least in India, a considerable floating population in the centers of economic activity, right? Let's move on. So some variables we will come at or look at. So this is P after n decades, population after n decades. Decade is equal to 10 years. 1 decade equal to 10 years. So, right, P naught or n equal to 0 right now, or at the end of the last known census years. N is equal to obviously the number of decades between now or this particular end of the last known census and the future point or time at which you want to calculate the population. X, different numbers or variables I understand, but these will be clear once we look at the simple example later. So average, which is arithmetic mean of the population increase in known decades, So let's say I look at it over 10-year period, let's say, right, or not 10-year, 30-year period. So per year, per decade, pardon me, you are going to have some increase, and the average increase over these 3 decades, that's what we have. That's the average arithmetic mean. So growth rate, this is depend upon the geometric mean, right? Geometric mean, yes, right, so on and so forth. And average of incremental increase of population in known decades. We will see why or how this comes into play. Let's look at some of the usual population forecasting methods. So here, okay, so what do we see? This should have been n. So this is arithmetic mean method. So what is this? We have a base population and it's growing at a constant rate. It as in the population is increasing at a constant rate. If I take it, if I take the derivative, right, with respect to x, okay, it's not with respect to x, I would say, okay, it's with respect to x, pardon me. So we see that it's a constant, right, it's just we assume it to be constant. So there is going to be a linear increase, let's say. So this is the case when it's, the city has been developed and occupied to the maximum extent possible, and there is more or less constant, what do we say, growth, or sometimes even I won't say decrease, but that's rarely the case, or even stagnation. So that's what you will see, or that's when you will employ this arithmetic mean method. But what about the case of Greater Noida, which we mentioned earlier, when we had explosive growth? So then we will look at this particular geometric increase method, as mentioned, or as we have or we do have here. It's for younger cities where, or especially those where people can see considerable what do we say, sources of income, and thus quite a few people coming in again, but rarely do we see this level of increase. If you take the natural logarithm and you look at that, you will see that it's more or less similar to the exponential growth here. Or let me take a shot at that. Okay, so I guess as you can see, it's exponential growth out here, right? R was the geometric mean. That's something that we saw earlier. N is the number of decades. P is the population at the last known census. Pn is the population after n decades, let's see. Another one is incremental increase, as in it's an increase, but it's going to not increase at a constant rate, but incrementally. So let's say 4, 3, pardon me, 4, 5, 6, 7. Again, I just use random terms, but you understand what I'm trying to get at. If you see the formula here, so this is for that arithmetic mean method, right? But here we also have this incremental increase terms, let's see, right? Or and this is for a city that's not too big, not too small, and has decent growth. And what is this term going to give you an idea about? The average value is added to the present population along with the average rate of increase, let's see, right? So again, I think once we look at the relevant data, it will be clearer, let's see. So this is that average increase, right? And then the average rate of increase also is being considered here in the second term. So looks like we have one particular set of data. The population of a town, right, as per census records is available, and assuming that the scheme of water supply will start from 1986. So this is back to the future. It is required to estimate the population 30 years from then. So 2016 still back to the future, and also the intermediate population after 15 years, right? So we are now in the past, 1986, and they want to use the data from 1921 to 1981 to get the data or forecast the population at 2016 and 2001. So we are going to look at all the three methods. So first, this is the data, 1921, 40, 44, so on and so forth, fine. And if I plot it, this is what I guess it looks like, right? You see that it's almost linear, if I may say so. Yes, other than during the initial periods, it's more or less linear. But again, we will not, look at this for now. But in general, if I had considerable information about the reasons for it, or reasons for this linear growth, and also looking at the economic conditions and the forecast, that's how you will be able to come up with a more educated guess. Yes. So what do we have here? We have the three formula for the three methods. Yes, constant increase, incremental increase, and more or less like compound interest. This is like simple interest, like compound interest, right? So arithmetic mean method, arithmetic mean, right? This is the population. So 44,000 minus 40,000 change, so 4,300. Same case, 60 minus 44, 16 I guess, 15,000 change, so on and so forth. The sum will be this, but I want to take the average of this. So 1, 2, 3, 4, 5, 6. 1,18,000 by 6. So that's what is going to be my constant, I guess, right? So that's what we see here. We are assuming that the population will increase each decade by almost 19,000 or almost 20,000. That's what we have here, right? So in 2001, because we were looking at 1981 data, right? 1981, so 2001, so 2 decades or 20 years. So what do we have here? So n is equal to 2. P naught at the end of 1981 was this. 2 decades, we are assuming that it grows at the rate of 19,769 per decade. So 2 times, and this is what I get in 2001, and I think next one was 2016 and 1981. So I guess 35 years. Yes. So 3.5 decades. Again, constant growth, assuming that it grows at this, what do we say, 20,000 people come into the city every decade, and thus we get it pretty simple, right? Let's move on to the geometric increase method and look at how to calculate that R or such. So here we have the population and rate of growth. Earlier we just looked at the actual what do we say, difference. Here the difference divided by the base. So 44,522 minus 40,185 by 40,185, right? That should come to this. Similarly, we have the rate of growth for that particular decade, right, for each decade, and then you will calculate R, the geometric mean, right? So geometric mean 1, 2, 3, 4, 5, 6. Yes. So what do we get? The geometric mean is 0.244. So in the previous calculation, we already looked at R by 100. Yes. If it was percentage growth, then we would have had to divide by 100 here, but we already calculated R by 100 earlier. Yes, that's what we have. For example, if we multiplied this by 100 to get percent, then I guess it would have been 10.8% here and 24% growth per decade, and then we would have had to divide that by 100. But again, we calculated R by 100 earlier. Again, different ways to go about it. It's just algebra, right? So using that, we can calculate the population in 2001 when n is equal to 2. Similarly, when n is equal to 3.5, we will plug it in and get this particular population. Then what about the incremental increase method? So this is obviously, all this part is similar to the arithmetic increase where we had the constant increase, I guess. Yes. So as you see here, we are talking about incremental increase, as we are assuming that each decade it will increase a bit more, incremental increase. So what is the increase in increase? So 15,000 minus 4,000, so 11,000, 15,200 minus 15,800, so decrease, right? 23 minus 15, 8, 25 minus 3, 23, 2, so on and so forth. And then the average increase in increase, or average, not average, total incremental increase is 30,000 over this period, right? So average of incremental increase of population, so that's what we have out here, and 6047. So that's how you calculate the y, right? So let's move on. So population in 2001 is equal to P naught 1981, n 2 decades, x, we have that average increase per decade. This we calculated when we were looking at arithmetic mean method. So n is 2, n plus 1 is 3, 6047 is what we calculated earlier, and now we end up with this, right? So similarly, again just plugging it in and getting the relevant value. So just to summarize, we have the population at the base year. Now each decade it's increasing at this constant rate, and from the decade after, right, after this first one, you see that its incremental increase is this. So that's why I guess we have to look at this particular aspect. Okay, I think one aspect that should have been looked at was, right, 1, 2, 3, 4, 5, 6 and 1, 2, 3, 4, 5. This is for the period after, so this should be by 5. So maybe a minor change in calculation, but you understand what needs to be done. So that's a change in aspect. It's the average here. It should have been 5, not 6, right? So about the 6 decades, average is this, or it's going to increase at this rate, and after, let's say, the first decade, it's going to increase by 30 by 5, I guess, right? So that's the rate at which it's going to the increase is going to increase after every decade, right? So that's something to keep in mind. Let's move on. So what do we have here? Comparison of the, what do we say, values we obtained from each of these methods. Let's just look at, let's say, 2016. So arithmetic mean, geometric mean and incremental. So obviously constant rate, relatively lesser value. Incremental increase, higher value, assuming that it's exponential increase, exponential, it will look like something like this. So that's what we have out here, right? Let's move on. Obviously, here we will see that relatively lesser disparity between the values, but as the time period increases, geometric mean is going to race ahead. That's what you would see, right? It's exponential growth out here, right? So let's move on. So per capita water demand. So we now know what period or until what period, and from that we know what population to cater to. Now that I know the population, I need to know per person, per day, what is it or what are the water requirements. So depending upon where they are, it varies depending upon the kind of water usage, but typically if it's in cities, you know more or less the functions that water is used for, and you can come up with an average value, right? So per capita water demand in India, it's around 135 liters per person per day, right? So for communities up to, again based on this reference, we know that for different types of communities based on the population, the consumption is relatively different, let's say. But in general, I believe 135 liters per capita per day, right? 135 liters per person or per capita per day, right? That's the average in India, but again you see that depending on the population it changes. And what is it typically used for? Urban and rural areas. Rural areas typically water requirements are less. We are talking about water requirement for personal use or such, or household use, not for agriculture or such purposes. So drinking water and such, cooking, fine, ablution, I guess they did not consider that here, but flushing of toilet here, it comes into play here. It depends on the kind of toilets and such, and kind of flushing systems that you have here, right? And bathing, again depending upon bucket, shower or such, and washing and such too, you will see that there is relatively supposedly greater requirement for water. So rural areas relatively less, urban areas relatively high. And other aspect is that you always need to be prepared for the contingency, not just the daily variation in water or need for water. So here you are going to look at firefighting demand that's required for firefighting. In India though, even if you provide the water, access to, or accessibility for the fire engines to the relevant areas is an issue. So that's why we hear such catastrophes and catastrophic loss of life in India. But again, that's a different aspect, I guess. At least firefighting demand, we need to be able to meet the need for firefighting, at least from the engineer's point of view. And again, you have different empirical formulae, and again P is in population, P is for population in 1000. So you can calculate this. I think they use this or these formulae in different exams, but it's not worth going into detail in this class here. But please be aware that there are different formulas and different limits and such. So with respect to industries, depending upon the industrial zone, again Greater Noida, some areas were earmarketed as industrial zones, and obviously for those zones you have to have some idea about what industries they are, and then you need to be able to provide the relevant water supply infrastructure, let's say. So again, that's why we see this here, again leather for 100 kgs 4, but again typical consumption is pretty high. Quality of paper or paper, relatively high consumption, but again note that the unit is different, right? You can't compare ton here and 100 kgs here, right? So but these are the different units. So per 100 kgs 4 kiloliters is required. Per ton of paper 200 to 400 kiloliters. And now the government is pushing for water recycle, such that net water requirement from the ground or such is relatively low or negligible for some kinds of industries, right? Let me move on. So variability in flow demand, right? What do we have out here? So as we saw for the wastewater, I think in the nights, this is the picture. Morning it increases, afternoon it comes down, there is a peak, again in the evening and such, and this is the cycle, I guess. But if this is the sewerage cycle, or the flow into the STP, obviously it is based on the water that's being used. So the water consumption pattern too will be similar to this. So there is obviously always going to be a variability in demand, let's say. So maximum daily demand, I think these are the ones or empirical relations that are used typically in India. So different countries, they use different relations. I think this is the one that's used in India, let's say. So how do we get the maximum daily demand? It is 1.8 times the average daily demand, let's say, right? And one aspect that I need to mention before I go further is that in India, how is it that water supply takes place, or how does it end up at the homes? So you have your water treatment plant here under pressure. Sewerage flows under gravity. Water, you are pumping it up, you need more energy obviously, because typically from low or lower head to higher head, right? It goes to your tanks, and from that, it comes to your particular pipe. So I need to supply the energy required, let's say. So under pressure, it's going to flow. So that's one thing. Or depending upon the type of system, before it goes directly from the water treatment plant to the homes, you will have underground reservoirs, let's say, UGRs, underground reservoirs. And from here, you will have, right at that place, what is called overhead tanks, right? Overhead tanks. And from these overhead tanks, the pumping will go, or, the water will be pumped to your particular home. So that's the typical, way. And because of this particular buffer capacity in either the underground reservoirs or the OHTs, typically, even though maximum flow is expected, or you need to look at that, that is typically taken care of when we look at the UGRs or OHTs, let's say, and also the pump capacity. So that's where it comes into play. That's something I wanted to mention. So maximum daily demand, maximum hourly demand of maximum day, right? So peak demand. So it seems it's considered as 1.5 times the average hourly demand. And we are getting this average hourly demand from this particular case, maximum daily demand, let's see, 1.8 into average daily demand by 24 hours per day. And from that, we get this 2.7 into annual average hourly demand, let's see, right? Or this, I guess, yes, you can look at the variables and see which one is equal to which one. So what do we have? Again, maximum weekly demand and maximum monthly demand. Again, these are all pretty simple, empirical, formula. It's not worth going into detail here. One aspect, as we also looked at earlier in the case of the CPHEO or other reference data, we see that as the population increases, the variability will decrease. As you can see, variability, it evens out, the variability decreases. So that's something to keep in mind. And design flow at the treatment plant, water treatment plant, what is it that we look for? Maximum daily flow and some safety factor. But with respect to the pumps, right, what do they need to be able to calculate or look at? Maximum hourly flow, right? This is with respect to hourly flow, and more importantly, to need the fire demand. So this is something that we need to consider, especially when we are looking at the distribution pumps or OHTs, let's say, right? Let me move on. So water quality standards, but looks like I spent considerable time in this session. In the next session, we will see what is the kind of water we need to supply. Until now, we have looked at how much water we need to supply, and the next session, we will see what is the kind of water we have to supply. As usual, thanking you for your patience.